sorry, eta is a 4 form. Then you have eta alpha, which by definition is E alpha in eta, which is the frame interior product with eta. So this is a 3 form, and you can go on like this. Then you get eta alpha beta by definition is E beta in eta alpha. So we have here a 4 form, here we have a 3 form, here we have a 2 form, now we get a 1 form, eta alpha beta gamma, by definition eta gamma in eta alpha beta. So we have here a 3 form, a 2 form, sorry. No, 1 form. 4 form, 3 form, 2 form, 1 form. And then we have a 0 form, which is then just one more index, alpha, beta, gamma, delta. That is by definition E delta in eta alpha beta. So this is a 0 form. And this is up to a constant equal, up to a factor equal to the Gravitation symbol times the square root of minus 30. So this is our eta basis, which we, for instance, this quantity we use for defining a Lagrangian for Einstein-Cartan theory. So these quantities play a quite important role in exterior calculus, and we have to be to familiarize ourselves with these quantities. We can prove that eta alpha is nothing but the Hodge star of theta alpha. And eta alpha beta, the 2 form, is the Hodge star of theta alpha, which theta beta, etc. It's always a Hodge star of the corresponding product of the equals. So this is sort of the just a remark, and in order one can decompose a connection in a Riemann-Cartan space in a Riemannian and in a non-Riemannian piece. This is only good if you want to compare your theory, if it's ready, with GR, for instance. But in working in H theory of gravity, we always have the gamma independent and the theta independent, the co-frame and the Lorentz connection. We don't want to decompose it because this because these are just the independent variables of gauge theory, and you also do not decompose the alien electromagnetic magnetism into different pieces in order to develop the corresponding theories. But it's good to know that we can decompose the connection, alpha beta. Since we have now a metric, we can always raise and lower the indices, and the metric is metric compatible, so it also commutes with the covariant derivative, so there is no, we can always put the indices up and down at our, how we want to have it. So the connection can be decomposed in a Riemannian connection minus, this is conventional, K, which is called the contortion, K alpha. This is the contortion. And this contortion is anti-symmetric in alpha and beta. So K alpha beta And we can, of course, then express the contortion in terms of the torsion. Let me just give you the formula. We have on the one hand side T alpha is a two form, so it's a one form K alpha beta, which theta beta, which you can prove by using this formula. And you can resolve it with respect to the contortion K alpha beta is equal E alpha in T beta anti-symmetric, and you get an additional piece which is which you can put in different forms. The form which I have used here is -1/2 times parentheses E alpha in E beta in always means inner product, and this I pronounce as in. The exterior product I usually pronounce as which. This is which. You know, this is just has a form of a wedge, the exterior product, and the interior product is in LaTeX, it's R-floor. Some people also take it, call it I, which I don't like, because you don't call the exterior product with E. Why should I call the interior product with I? I don't know. And also it is very, then you have indices of indices, and then it's very hard to read. What did I stop here? In the torsion, T gamma, parentheses. Now this is, torsion is a two form, two inner products make it a zero form, and then you have to blow it up again. Theta gamma is a one form. So this is the reverse of this formula. So you can always express the torsion in terms of the contortion or vice versa. It has the same number of independent variables, 24, and this is a one form K. The one form has 4 independent components, and here the indices are 2, and they are antisymmetric, so it's 6 times 4, it's also 24. So you have 24 independent components of torsion or contortion.
I think
something wrong?
Yeah, the co-Friedrich wedge was torsion first, and then take inner product.
Sorry?
The last parentheses.
This?
Yeah, it should be T gamma wedge, theta gamma first.
I mean, you can take, you have first to take this product and then the second product.
Oh, but I remove it from your paper.
No, you can, if you can transform it, you can bring this theta inside and partially differentiate.
Oh, okay.
This is exactly the form which if you had used this form, you had immediately seen that the variation with respect to theta is isolated here, you know. So this is an alternative form. There are 2 different forms of the same unit. I gave now here the form that you could have used in order to have this proof, you know what I mean. So this is correct. At least I took it from my manuscript, and I think this is correct. Okay, now, and this brings me already to what is, for formulating theories, it's important to get a little bit of understanding of this abstract space. We all have a sort of understanding of Riemannian space. It has 10 metric components. You have the connection, which has 40 components. You have the geodesic. But here, this space is much more complicated. And so it's better to bring a little bit order in this space in order to, also, I mean, you can learn these things, for instance, this can be applied in a certain way to dislocation theories, continuum theory of dislocations in 3 dimensions. And in these 3 dimensions there are also very nice pictures for different quantities. So what I'm just shortly mentioning is that we can now torsion and curvature, which are the peak strengths and which we need to understand, we can irreducibly decompose it easily into different components. And for the torsion, irreducible decomposition under the Lorentz group, decomposition of torsion. Now the torsion is, as we know, a two-form. P alpha equals 1/2 times T, say, beta gamma alpha theta beta, which theta gamma, if I decompose it into its components. And the torsion is, of course, the torsion components. This is gamma. This is just a two-form developed in the beta basis, in the theta basis. Okay? This is anti-symmetric, so it's anti-symmetric in these 2 indices, and you see it in indices much easier than in the exterior calculus. If you lower this index, then you have a totally anti-symmetric piece, which is irreducible, and you have the trace of the torsion. Whether you take the trace with respect to the first or the second index doesn't matter because it's anti-symmetric. So you easily see you have how to decompose it. So T alpha can be decomposed into 3 pieces. The tensor piece, T alpha plus the trace piece, T2 alpha plus the totally anti-symmetric piece, T alpha. And we call this, because we have computer programs which do these decompositions for us, this is torsion is equal, we call this the tensor piece, tentor. This we call the vector piece, trace or vector piece, trator or vector. We write it with K in order not to distinguish it from an ordinary vector, plus axial vector, excitor. These are our computer names, and these are 24 components, these are 16, these are 4, and these are 4. And you can easily convince yourself that if you define the vector piece as follows, V by definition E beta in T beta. So this is this is a 1 form, and it has no indices left. And then you can easily prove that T2, the vector piece of the torsion, is equal to minus 1/3 times V which theta alpha. And in a corresponding way, you can, the axial vector is by definition the parenthesis theta, you kill the index theta beta, which T beta. So this is a 3 form, you take the Hodge dual, you have a 1 form. So you have again a 1 form, and the T3 can then be expressed as 1/3 times star parenthesis A which theta. So we have, I hope this is plausible, that we have a vector and the axial vector piece, and of course is if you in Einstein-Cartan theory, which we discussed already, we have a spin contact interaction, and this spin contact interaction has for a Dirac spin or vector pieces and axial vector pieces. So you get VA interaction, VV interaction, AA interaction, depending on the parity. So these names are deliberately chosen in order to get insight into if you investigate. And I, at my end of my lecture last time, I gave you 4 papers from 2012 and 13, where this spin contact interaction has been investigated in detail within Einstein-Cartan theory, and there this vector and axial vector, these are both one forms. One forms have 4 components and are dual to a vector, so these are covectors, basically vector and axial covector. Okay, so and you have very nice visualization in 3 dimensions in terms of O dislocations and H dislocations. Just to mention these H and O dislocations. No, screw, C. Okay, and in the same way I want to discuss the curvature. Well, the curvature can be decomposed into 6 independent components. And of course this is a bit complicated, but okay, well, it's not simple. I mean, in principle it's very simple, but you have to do a little bit work in order to understand. I runs from 1 to 6, and I call the different pieces Ri, alpha, beta. Now, the curvature tensor is a 2-form. And a 2-form, so it's anti-symmetric, so if you write it in indices, R alpha beta is 1/2 times R mu nu, alpha beta times theta mu which theta nu. So it's anti-symmetric in these 2, but in the Riemann-Cartan space also anti-symmetric in these 2 indices. In 4 dimensions, anti-symmetry means 6 independent components. So it's a 6. You can represent it by a 6 times 6 matrix, which has 36 independent components. So you have here 36 independent components. In Einstein's theory, these 2 index pairs commute, which you learn in Einstein's theory. One of the first exercises for handling the curvature tensor is one of the algebraic properties of the curvature tensor. So in Einstein's theory, this is a symmetric 6 times 6 matrix, so it has only 20 independent components. In Einstein-Cartan, in Poincaré-Gates theory, it has 36 independent components. And now let me write out the 6 independent pieces. 3 are familiar to you, if provided you are familiar with general relativity, and 3 are new, and the new ones are also familiar to you if you think a little bit, and if you help me to think a little bit. So the first irreducible piece is right in Einstein's theory. It is called Weil piece, and is defined, as we will see in a minute, exactly as in Einstein's theory. The Weil piece has 10 independent components. The second piece is not present in, I mean, this is of course conventional, what we call second piece. We ordered it according to a certain principle, which is called, we call it air-com. Air-com. Air-com means in Einstein's theory, both pairs commute, but if they don't commute, you get some kind of construction like R alpha beta mu minus R mu times alpha beta. And if you find out a construction, so it measures how much the comparison, the commutation of two index pairs is violated. So this is a pair it has 9 independent components. And the third one is very easy to explain, R alpha beta. It is what we call the p-scalar, pseudo-scalar. This is just the proportional to R in a Riemann-Cartan space. You can build a totally anti-symmetric piece, and that this is irreducible is clear. It has one independent component. In Riemann space, this vanishes. So we have here two pieces which are non-Riemannian. This is non-Riemannian, this is non-Riemannian. This is the totally anti-symmetric piece. It's one of the algebraic identities in Riemannian space, and this is 0. And the other one is this algebraic pair commutation. It's also clear in Einstein's theory, this is 0. And you have the while, which is like in Einstein's theory. And then you have R4, which you have in Einstein's theory. It's in Riemann-Cartan space. The Ricci tensor is defined as follows. We have the curvature 2 form, and we can define the Ricci 1 form. Ricci 1 form is rich because R is already taken, we take rich. Rich alpha is by definition E alpha by E beta in R alpha beta. R alpha beta is the curvature 2 form, inner product gives a 1 form, and this is a Ricci. And if you take the components of the 1 form, you have 2 indices here, it's Ricci. And this is really the Ricci tensor, but the Ricci tensor in Riemann-Cartan space, as you can easily convince yourself, is asymmetric. It's no longer symmetric. So the Ricci tensor is asymmetric, and this piece R4 is just a symmetric piece of the Ricci tensor. We call it rich symmetric piece, but it's also trace-free. We can, of course, remove the trace because we want an irreducible decomposition, so we call it rich sim-free, which is, of course, a symmetric trace-free tensor in 4 dimensions has 9 independent components plus R5. We will use these pieces next time in order to discuss general Lagrangians, so I need to define these pieces. And this is just the antisymmetric rich anti, which has this antisymmetric piece in with 2 indices 6 in 4 dimensions, and then you get the curvature scalar, which we call R6. Alpha beta, this is scalar, which we have also in Einstein's theory. Which is it's also sometimes called scalar. So you have here a decomposition into 10 plus 1 plus 1 plus 9 plus 1 plus 9 plus 6 plus 1. So this is an irreducible decomposition. And of course, now you can specialize your spaces, and we, in these theories, one looks for exact solutions, and the most simple one is, of course, if you kill certain pieces in a more or less systematic way. Okay, this is what I wanted to say about the geometry, which is more what I really took me more time than I really thought it was. Now we take matter 5.2 matter fields in the Riemann-Cartan arena. Matter fields in the Riemann-Cartan arena. Of course, later the matter acts back on the arena and deforms it like in any decent gravitational theory. But we choose, as we already said, orthonormal frames. Sheet alpha beta. This is O alpha beta. Those frames here. This is diagonal. And then we have our meta-Lagrangian. Meta-Lagrangian. L is equal L. Well, a metric is trivial, but the coframes, and of course the meta fields, psi capital A, and then the connection cannot appear because it has to be tensorial, so it can only appear in the form of an exterior derivative, covariant derivative of the psi A's. And for convenience, we also allow non-minimal coupling T alpha R alpha beta. I'm not really seriously investigating non-minimal couplings, but it will turn out to be very convenient if we derive the Noether identities and afterwards put the psi equal to 0, then we have at the same time also the Noether identities for the gravitational Lagrangian. So for that reason I carry the curvature and the torsion. These are non-minimal pieces. Minimal coupling means that the connection only enters via the covariant exterior derivative. The non-minimal coupling means, like in electromagnetism, you have the minimal coupling that the derivative, partial derivative minus I times E times the vector potential,